Dear students, last time we have discussed the chemistry of organometallic compounds, in which we have discussed what is meant by pi-acid ligands, synergism. Then we have also discussed what are metal carbonyls, their method of preparation, and various reactions shown by these metal carbonyls. Today we are going to discuss the transition metal alkyls and their classification. Classification of transition metal hydrocarbons we are going to discuss. Alkyls, aryls of transition metals. So friends, these are the organometallic compounds which have metal carbon, and that is sigma bond. So they contains metal carbon sigma bonds. Let us see here the main group elements alkyls and aryls. See, this is dimethyl zinc, then diethyl zinc. This is mercury compound, tin compound. This is trimethyl boron, RMGX, ARMGX. There are large number of examples of alkyls and aryls. The bond between transition metal and carbon, these are very strong. Energy is 125 to 270 kilojoule per mole. So they are very strong bonds. Let us see next point, stability of transition metal alkyls. These transition metal alkyls are unsaturated and therefore various pathways requiring lower activation energy for their decomposition. So these different pathways of decomposition are available to synthesize stable transition metal alkyls. Let us see first pathway, which is important one. It is called as beta elimination. This is the most common pathway for decomposition of transition metal alkyls. In this method, what happens? Metal alkyl is converted into metal hydride. Okay, metal alkyl is converted into metal hydride complex. Hydridometal alkene complex is the intermediate. This beta elimination takes place when, point number 1, when the beta carbon atom of alkyl group must have at least one hydrogen atom. So, condition number 1, beta carbon atom of alkyl group, it must contain at least one hydrogen atom. Second condition, metal carbon, carbon hydrogen unit. This must acquire syn coplanar conformation. Due to this, what happen? Beta hydrogen atom come closer and closer to the metal atom. This is again second important condition for beta elimination. Next condition, there must be vacant coordination site on metal atom, and this vacant coordination site is cis to alkyl group. It is must be situated at cis position to the alkyl group. Let us see with the help of example, or let us see steps in beta elimination. This is the transition metal alkyl. See this is CH2CH, this is beta carbon atom, and see this contains one hydrogen atom. Beta carbon atom contains one hydrogen atom, and see here vacant coordination site is shown, which is present on this metal atom. This is cis. Okay, this site is present cis to this alkyl group. Okay, these are the conditions. Then see, in first step, what happened? This hydrogen okay, acquires this position, vacant coordination site. And here there is formation of this transition state, in which we have shown that this hydrogen is now attached to this metal atom. Okay, it acquires that vacant coordination site. Next one, see now, hydrogen atom is attached to metal atom. Here this is the alkyl group. So this is called as intermediate state. Hydridometal alkene complex is formed, which is decomposed, and here there is formation of propene, and in this way transition metal hydride is separated. So in this beta elimination there is formation of metal hydride, and here there is formation of propene. In this reaction, there is formation of metal hydrogen bond because there is formation of metal hydride. C pi bonds, and there is a dissociation of metal carbon and carbon hydrogen bonds. Intermediate contains 18 electrons. Instead of 16, they contain 18 electrons. That means 2 electrons are more than starting transition metal alkyl, which contain 16 electrons. And this undergoes beta elimination. And this pathway requires lower activation energy. This is very important. For this beta elimination, we require lower activation energy. Next point, but if transition metal alkyl contains 18 electron, at that time such type of transition metal alkyl does not show beta elimination reaction because intermediate have 20 electrons and higher energy, and due to which what happen, there is increase in energy of transition state and it decreases the rate of reaction. Next reason why 18 electron transition metal alkyl does not show beta elimination reaction. Next reason, these 18 electron transition metal alkyl, these are saturated, and in case of these no vacant coordination site is available on metal atom. Just we have discussed, there must be presence of vacant coordination site on metal atom. Then and then the hydrogen atom which is present on beta carbon atom, it acquires that position, that vacant coordination site. Got it? And in this way 18 electron transition metal alkyl does not show beta elimination reaction. Still, some 18 electron alkyls show beta elimination by using following steps. See, which are that steps? See here, this is the transition metal alkyl, here there is L dash, this is 18 electron complex. Slowly it separated this ligand L dash. So L dash which is present in this 18 electron alkyl, it is separated. That means here there is formation of vacant coordination site. And now due to that the complex has 16 electron. Then in this vacant coordination site this hydrogen is now present which is attached to this metal atom. Got it? So here in this case hydrogen atom is now attached to metal, and see now here this is the intermediate state, and see now here hydrogen atom attached to metal atom, and this is the alkyl group containing 18 electron. And from this intermediate state what happened? Alkyl group CH2 is separated in this way. And now when CH2 group is separated, here again there is formation of vacant coordination site, and this complex 16 electron complex is treated with L dash, and that vacant coordination site is now occupied by L dash, and in this way there is formation of 18 electron complex. Some transition metal alkyls cannot undergo beta elimination reaction, still they are stable and synthesized. They cannot undergo beta elimination reaction because first reason, they do not contain beta hydrogen atom and they are kinetically stable. Let us see the example. See this hexamethyl tungsten. Then this compound methyl is attached to manganese as well as 5 carbonyls. This is titanium compound. So these do not contain beta hydrogen atom and they are stable one. They do not undergo beta elimination reaction. Next reason, these transition metal alkyls cannot acquire syn coplanar conformation. This one MCCH. Okay, it is required because these hydrogen must be present at cis position of metal atom. So as this conformation is not present, so it cannot undergo beta elimination reaction and stable. See this example. In this example, we observe that there is no syn coplanar conformation and it not undergo beta elimination reaction. In this transition metal alkyls, beta hydrogen atom not approaches to the metal atom and therefore these are kinetically stable. These are again the examples which explain why they not undergo beta elimination and they are stable. Next one, the transition metal alkyls with 18 electron not dissociate to produce vacant coordination site on metal atom not shows beta elimination reaction and therefore they are stable. We have discussed for beta elimination reaction there must be vacant coordination site, but for this one, these are the examples. For this transition metal alkyls there is no vacant coordination site and hence this transition metal alkyls cannot undergo beta elimination reaction. So this is about beta elimination reaction. Next one, second, fluoride elimination. The transition metals like scandium, titanium, vanadium, chromium, manganese, that means the elements which are placed at left side of first transition series. Then lanthanides, actinides are the hard Lewis acid and these hard Lewis acid they show strong tendency to combine to react with hard Lewis bases like fluorine. We know that in chemistry SHAB concept is very important. Soft and hard acids and bases. That means hard acid combined with hard bases, soft acid combines with soft bases. So here as these elements that we have discussed, that elements lanthanides, actinides, these are hard Lewis acids, they are combined with hard Lewis bases like fluorine. In this, what happened? The metal fluorine bond energy is high and therefore these elements are not able to form stable fluoroalkyls, and in this way they undergo beta elimination of the fluoride. Okay, there is beta elimination of fluoride, therefore this elimination is called as fluoride elimination. See this example. So this is LNM, CF2 group, fluorine is at beta position and here this is the vacant coordination site. It is same to that of beta elimination. Here there is vacant coordination site. At cis position of metal atom there is fluorine. So in next step what happened, this fluoride ion is attached to metal atom. Okay, in this way this is the intermediate step, and then here it decompose, and in this way here there is formation of metal fluoride, and this is the byproduct. CF2 is the byproduct. While the transition metals present on right side of transition series, above reactions we have discussed for the metals, for the elements which are situated on left side of transition series. But when the metals are present on right side of transition series, they form weak metal fluorine bond, and hence they form stable fluoroalkyls. Because what are the reasons? First one, lack of beta hydrogen atom in CF2 group. There is no presence of beta hydrogen atom. Second one, the bond between metal and carbon, it is very strong. Why? Because filled atomic orbital of metal atom and vacant sigma star molecular orbital CF bond overlaps, and there is formation of metal to ligand pi bond, which is very strong one. Got it? And due to this reason, there is formation of stable fluoroalkyls by these elements which are present on right side of transition series, while the elements present on left side undergo beta elimination, and there is separation of fluoride compound. So this is about fluoride elimination. Next type of elimination, reductive elimination. This is the pathway for again decomposition of transition metal alkyls. The transition metal alkyl hydrides with cis hydrogen and alkyl groups are unstable. Due to this, what happened? They are unstable, and therefore they undergo reductive elimination. See this reactions. This is the alkyl complex having 18 electrons. To this methyl group at cis position there is hydrogen. Okay, so there is reduction, and CH4 is separated from this compound, and in this way this transition metal alkyl is formed. Similarly, cis dialkyls also undergoes reductive elimination, and there is formation of alkane molecule. See this compound, transition metal alkyl, 18 electron compound. Here this is the this is the alkyl, this is the alkyl group. So dialkyl. Okay. So this compound undergoes reductive elimination, and hence here there is formation of alkane. 16 electron complex is obtained. Then see next point. Classification of sigma bonded transition metal hydrocarbyls. They are also called as hydrocarbyls. First, this classification is done on the basis of nature of groups attached to the central atom. So type number 1 again, homoleptic organometallic compounds. These compounds contains same organic groups. So same organic groups are attached to the metal atom, and at that time they are called as homoleptic organometallic compound. Example, see here, only methyl group is attached to tungsten. In this case, same methyl group is attached to titanium. In this case, again methyl group is attached to neodymium. Okay, and in this way this is called as homoleptic organometallic compound. Next type, of course, it is called as heteroleptic organometallic compound. When more than one type of groups are attached to central metal atom are called heteroleptic organometallic compounds. Different type of groups are attached to the metal atom. That means more than one type of groups are attached to central metal atom. They are called as heteroleptic organometallic compounds. See this example. Tantalum is attached to chloride as well as with methyl. Here also titanium attached to chloride as well as methyl group. This manganese is attached to carbonyl and methyl group. Got it? And therefore, these are called as heteroleptic organometallic compounds. So this classification is done on the basis of nature of groups attached to the central atom. Next point or next classification on the basis of number of metal atoms per molecule. How many number of metal atoms are present in that organometallic compound? On the basis of this, there is classification. So first one, mononuclear organometallic compounds. These have only one metal atom per molecule. Again see, this is pentamethyl tantalum, only one tantalum. Hexamethyl tungsten, only one metal atom. Tetramethyl titanium, only one titanium metal atom is present. So these are called as mononuclear organometallic compounds. And second type is polynuclear organometallic compounds. They have more than one metal atom per molecule and form through bridging alkyl or aryl groups, and there is metal-metal interaction. Got it? So, more than one metal per molecule is present and their alkyl group and aryl group acts as bridging groups. See, this is the example here. Methyl group is acts as bridging group. Here, this is the metal. Got it? Hence, it is belongs to this type polynuclear organometallic compound. Similarly, see here chromium, more than one metal atom is present, and here see these types of alkyl groups are present. They are acts as bridging molecules between the two chromium atom. So this is about classification. Now see next point, general methods of preparation of transition metal alkyls. First method to prepare transition metal alkyl. Alkylation by other metal alkyls. In this case, transition metal halides are reacted with Grignard reagent or alkyls or aryls of reactive metals like lithium, magnesium, zinc, aluminum, tin in solvent dry ether, or we can say non-protic solvent, or hydrocarbon, and then transition metal alkyls or aryls are produced. This reaction is also called as halide carbanion exchange reaction. So in this case, what we have to do? Transition metal halides are reacted with Grignard reagent or alkyl aryl of reactive metal like various metals we have to use lithium, magnesium, zinc, aluminum and tin in non-protic solvent, and then there is formation of transition metal alkyl or aryl. See, these are the examples. This is the transition metal halide titanium tetrachloride reacted with lithium methyl, okay, in ether at 80 degrees centigrade. Hence this is the formation of tetramethyl titanium. Next one, again titanium tetrachloride reacted with C6H5CH2MgCl in ether at this temperature minus 60 degrees centigrade. Again there is formation of transition metal alkyl. This is titanium alkyl. 4MgCl2 is the byproduct. Next one, zirconium tetrachloride reacted with this type of reactant in ether, and there is formation of this transition metal alkyl, zirconium alkyl. Again same byproduct is obtained. tungsten hexachloride reacted with again lithium trimethyl in ether. So hexamethyl tungsten is obtained. LiCl is the byproduct. So in this way, these are the another examples. Okay, and transition metal alkyls or aryls are produced. Then see next method of preparation of transition metal alkyls. Reaction of sodium salt of anionic complex with alkyl or aryl halide. So when sodium salt of anionic complex reacted with alkyl or aryl halide, at that time transition metal alkyl or aryl is formed. See, this is sodium ion. So salt of anionic complex. So sodium salt Na, manganese pentacarbonyl, this is anion, plus CH3I, that means alkyl halide. So what happened? Here there is formation of this transition metal alkyl. Manganese is attached with methyl group as well as with 5-carbonyl. So transition metal alkyl is obtained. This is the byproduct. Sodium iodide. This is the type of SN2 reaction. Mechanism of above reaction. So this is the cation we have discussed. Manganese is attached to 5-carbonyl group. On manganese there is negative charge. On sodium there is positive charge. This is CH3 iodide ion. How CH3 manganese, that means transition metal alkyl, is separated? How this iodide is separated and reacts with sodium, that is shown in this reaction. So here there is formation of transition metal alkyl and sodium iodide is the byproduct. Then see next method to produce the transition metal alkyls, which is called as oxidative addition reaction. So with methyl iodide, unsaturated complexes undergo this type of reaction, and at that time there is formation of transition metal alkyl. See here, this is the complex, 16 electron complex, coordination number of iridium is 4, oxidation state is 1 when reacted with methyl iodide. So see here, iridium is now attached with the CH3 as well as iodide ion. This is 18 electron complex, coordination number of iridium is 6 and oxidation state is 3. So this is called as oxidative addition reaction, and in this way CH3 group is attached to iridium. In this way transition metal alkyl is obtained. Next see, the unsaturated complexes containing water H2O as ligand shows oxidative addition with methyl iodide again. Again there is formation of transition metal alkyl. See here, this is chromium, oxidation state is 2, attached with 6 water molecules, charge on this complex ion is +2. When reacted with methyl iodide, what happened? One of the methyl group is inserted in this square bracket and water molecule is repulsed. Okay, on this square bracket there is +2 charge. This is transition metal alkyl, and here to this water molecules are attached to chromium as well as iodide is inserted in this complex ion, and these two water molecules are separated. Got it? Then see next reaction, metal atom reaction. Transition metal vapor when condensed in presence of alkyl or aryl halide, transition metal alkyl or aryl is formed. So see on palladium, 0 oxidation state. So CF3I is reacted with this palladium. There is change in oxidation state of palladium. Okay, at that time this transition metal alkyl is obtained. Iodine CF3 are inserted or reacted with palladium. So transition metal, that means palladium, is present in vapor form. Similarly, here nickel is present in vapor form. They are condensed with this halide, alkyl halide. Okay, ethyl bromide is reacted with nickel vapors in presence of C6H5Me. This reaction is done at minus 196 degrees centigrade, so that nickel bromide is the byproduct and this is the transition metal alkyl. In this way, there is formation of transition metal alkyl. So students, we conclude this lecture here. In next time, we continue the remaining methods of preparation of transition metal alkyls. Thank you.